If pH drifts outside a 0.3 unit band, coagulation fails. Beyond 0.5, the entire downstream process collapses within hours. Industrial wastewater enters these plants carrying thousands of milligrams per liter of suspended solids. It leaves at under 5. That's not one machine. It's a chain of 6 chemical and physical stages, each with its own failure window, each dependent on the one before it. One droplet will pass through screens, pH correction, coagulation tanks, flotation cells, and 2 membrane barriers before it's clean enough to reuse. Today, we follow that droplet, stage by stage, tolerance by tolerance. Industries generate over 380 billion cubic meters of wastewater every year. Less than 20% is properly treated and reused. The rest gets discharged into rivers, oceans, or evaporation ponds. For facilities that do reclaim their water, the economics shift dramatically. Freshwater intake drops by 70 to 90%. In water-scarce regions, that's the difference between operating and shutting down. But industrial wastewater isn't municipal sewage. It contains oils, heavy metals, dissolved salts, and chemical residues that household systems can't handle. Cleaning it requires precision measured in pH units, micrometers, and seconds. Skip any stage, and the water can't be reused. Worse, it damages the equipment meant to clean it. Our droplet arrives through collection pipes mixed with debris from across the facility. The first barrier: coarse bar screens. Steel bars catch large fragments, rags, plastic, metal shavings. Next, fine screens with millimeter-scale openings remove smaller particles. This isn't filtration, it's protection for everything downstream. Automated raking systems clear the screens every few minutes. Differential pressure sensors trigger cleaning cycles when flow resistance rises. A single piece of plastic film can blind an ultrafiltration module. Recovery time, 4 to 12 hours. Screening removes less than 5% of contaminants by mass. But without it, pumps erode, seals fail, and membranes foul before they ever reach design capacity. Our droplet passes through, the debris stays behind. Industrial discharge doesn't arrive at constant flow or constant chemistry. A batch release can spike flow rates by 300% in minutes. A cleaning cycle can swing pH across the entire scale within the same hour. The equalization tank absorbs these shocks. Mixes run continuously, preventing settling and ensuring chemical homogeneity. The tank blends high pH and low pH streams over hours. Without equalization, downstream pH control can't react fast enough. The system chases spikes instead of holding steady. Our droplet spends 6 to 12 hours here, blending with thousands of others until the chemistry stabilizes. What exits isn't uniform, but it's predictable. And predictable is what the next stage requires. Here's where chemistry begins, and where most invisible failures start. Coagulants only work inside narrow pH windows. Aluminum sulfate, 6.0 to 7.5. Ferric chloride, 5.5 to 8.0. Outside these ranges, flock formation fails. Inline sensors sample the flow every 1 to 2 seconds. Dosing pumps inject acid or caustic within milliseconds of detecting drift. The target band is plus or minus 0.3 pH units. That's tighter than most laboratory experiments. Drift beyond 0.5 units, and coagulation efficiency drops by 30 to 50%. The flocks that form are weak, small, and shear apart under flow. The water looks identical. But 30 minutes later, the flotation tank underperforms. 2 hours later, membranes start fouling. Our droplet passes through at pH 6.8, right in the center of the window. The chemistry is now primed. Suspended particles carry a negative surface charge. This charge keeps them repelling each other. Stable in suspension, impossible to remove. Coagulants neutralize that charge. Our droplet enters a rapid mix chamber. Aluminum sulfate releases positive ions. The repulsive charge drops to near zero. Particles can now collide and stick, but they're still microscopic, too small to separate. That's where flocculants enter. Polymer chains are added in a slow mix chamber. They bridge neutralized particles into larger aggregates, visible flocks that can be captured. Mix too fast, and hydraulic shear breaks the flocks apart. Mix too slow, and bridging never completes. Optical sensors monitor flock size in real time, Dose rates adjust every 30 to 60 seconds based on incoming turbidity. Our droplet is now attached to a floc cluster. What was invisible is now physical, ready for separation. The flocculated stream enters the DAF tank. A side stream is pressurized and saturated with air. When released into the tank, dissolved air comes out of solution, forming microbubbles smaller than a human hair. These bubbles attach to floc particles. The combined density drops below water. Flocs rise instead of sink. A skimmer blade sweeps the float layer into a sludge trough every 10 to 20 seconds. Too little air and flocs sink, accumulating as sludge. Too much air and turbulence resuspends particles into the flow. DAF removes over 90% of suspended solids and up to 99% of oils and greases. Retention time: under 30 minutes. Our droplet separates from its floc. The solids float upward. The water continues forward, visibly cleaner, but still carrying dissolved contaminants. So far, we've removed what we can see: solids, oils, suspended particles. But dissolved ions, salts, and molecular contaminants passed through every stage untouched. Now we fight what's invisible. The membrane stages begin. Our droplet enters the ultrafiltration system. UF membranes have pore sizes small enough to block bacteria, viruses, and colloidal particles. Water passes through the membrane walls. Solids stay behind. But here's the hidden engineering problem: fouling. Organic compounds absorb onto the membrane surface. Biofilms develop. Colloidal particles clog the pores. Flux drops. Pressure rises. Eventually, the membrane blinds completely. If transmembrane pressure exceeds 1.5 bar despite backwashing, the membrane requires chemical cleaning or replacement. Backwash cycles run every 15 to 60 minutes, reversing flow to dislodge deposits. Chemical cleans run every 1 to 4 weeks. Membrane modules cost $50,000 to $200,000 each. Detecting fouling early extends lifespan by 30 to 50%. Our droplet passes through. Turbidity drops below 0.1 NTU, but dissolved salts remain, and for high purity applications, that's not clean enough. Reverse osmosis operates on a different principle. UF blocks particles by size. RO rejects dissolved ions through diffusion across a semi-permeable membrane. Operating pressure: 10 to 25 bar, high enough to overcome osmotic pressure and force pure water through while salts stay behind. Salt rejection exceeds 98%. Permeate quality: total dissolved solids below 50 milligrams per liter. But RO membranes are vulnerable to two threats: scaling, when dissolved minerals exceed saturation and precipitate on the membrane surface. Antiscalants are dosed continuously to prevent buildup. Biofouling, when microorganisms colonize the membrane. Non-oxidizing biocides are dosed intermittently. Chlorine would destroy the membrane material. If salt rejection drops below 97%, the membrane is degrading. Conductivity sensors monitor permeate quality in real time.